Works. So the third speaker of today's session is Jori Mitsutani. Jori is doing his PhD over here at the University of St. Gallen. And he is concentrating on how to integrate DevOps with cyber-physical systems. And Jori, we're looking forward.
Thank you so much, Simon, for introduction. So I'm Jori, and greetings to someone watching from remotely. And this is a collaboration work from Ganesh sitting over there and with my supervisor, Simon. And in snippet, our research is about the engineering tasks required to operationalize industrial cyber-physical systems. And this process is implicated and time-consuming, so tedious. I want to solve this. And to this end, we leverage DevOps, a collection of software service development and operational tactics to better coordinate this engineering workflow. And this also establishes the structural knowledge transfer among multidisciplinary stakeholders, and therefore would lead to reduce the time it takes to finish the tasks done by humans, right? And let's begin with the DevOps and also IT/OT convergence. The DevOps principles have been developed to manage the development and operation phases of software services, usually on cloud infrastructure. And on the other hand, in the industrial CPS, we have field devices and controllers, and they are forming complex topology and therefore require IT and OT convergence. What it means is that we have traditionally have this automation pyramid and where the boundary of IT and OT were clear. But nowadays, thanks to the unification efforts done by the OPC Unified Architecture, for example, we are seeing this convergence of IT and OT domains because the older functional entity in the different layers are interconnected. So it is kind of hard to differentiate them now. And I see an analogy here because the DevOps trying to merge these different phases, planning and DevOps and Ops. And the IT and OT convergence are also trying to do the same, right? We have to solve this problem anyway. And I want to define what the offline and online engineering that exists in industrial CPS. Engineering tasks have two major aspects, which is to design the system offline before doing anything at all. So let's take a look at this example on the right-hand side. We have this small mock system consisting of, so let's think about small enterprise, and we have robotic arm and end effector in the factory cell, and which is in the building facility so that we have electric room and also have server room, which has a network appliance and servers. And to make this whole system online, we start with wiring and installing the devices on the shop floor. So which takes a human effort, of course, but in addition to it, we also have the telco lines to connect the networks and bring it to the internet if necessary. And also to power them on, we need electricity. So we need these electricians to do the work. And this is not the end because they are also multidisciplinary. This involves a lot of human roles and multidisciplinary domain experts and technicians, which means in the baseline, we have this platform for robotic arm, which has a specific requirement for the vibration resistance, for instance. And in this case, we have to manufacture a specific platform, which is derived from this CAD data. And similarly, the mechanical engineers have to follow this instruction to mount the robot following the safety guidelines. And electrical engineers have to look into the documentations to figure out which I/O to use and also figure out which cables are needed to power and connect the controller. And to power this controller, there is a maybe specific type of electric outlet coming from building facility. And this building facility also have some user interface to monitor the energy consumption of this building or in this shop floor in this specific factory cell. After taking care of this, the robotics engineer might need to calibrate the parameters that is needed to guarantee the functional requirement. And all the construction design of this building passing through the Ethernet cable to the server room and maybe needing a specific type of mounting rails to install the network switches and routers. And finally, network engineer can configure the management of the network appliances, and all the cool things can be coded as a software and deployed in the server. So as you can see, these engineering work are quite multidisciplinary, and such work accounts for a large part of commissioning and maintaining the system, and consequently necessitate extensive human efforts to document and discover the data that exists in this CPS. So data provenance, in earlier this year, we also discussed this, and which is quite important to give the transparency in the system and for the reliable and more flexible system to sustain for more flexible business use cases. Okay, that's the engineering part. But today, I want to look into the process to enable such CPS, right? And the phases start from conceptualization of the system, and which involves stakeholders who are the project owner or domain expert in multiple domains. And after conceptualization, they proceed to the installation phases, which also employ technicians to do the job. And if necessary, they go back to the previous phases in conceptualization and fix something and move it on. Likewise, they move on to configure the devices and commission the system, right? During these phases, or even in between the phases, they create artifacts. And this artifact, the plan artifact, involves the requirement documentation or quotation of the field devices that they need to buy from the vendors. And the design artifact has the specification, which specifications to follow, and maybe handwritten drawing to give the ideation of this system. And engineering information has more concrete information about this system, such as a floor plan of this factory and Gantt chart for the logic that's deployed to the firmware, or network topology of this building. From this information, we can derive machine-readable data, such as building information model or automation ML to describe the field devices and functional entity, or Collada for the 3D applications, and maybe netconf for the management of the network appliances. Now, you see this cyclic coordination of these phases and artifact creations, but unfortunately, these are segregated and there is no systematic way to achieve it. So what we do is this domain expert and technician talk to each other, having a call or exchange emails or in-person meeting, and nobody likes it because they want to do it in a more efficient way and more secure way that they do not have the mental insecurity, right? So the question is, can we manage this cyclic coordination in a systematic way? To summarize, we established these two research questions. How can we integrate and coordinate the multidisciplinary engineering task in a deterministic total cycle time? Second one is, how can we exchange this information and support humans to execute the engineering task in a systematic way? To answer these questions, we have 4 building blocks. The first 3 are from the DevOps principle, and the last one for something else. We'll show you in the next slides. CI/CD pipeline is one aspect of DevOps that enables the continuous integrations of the software services, and which enables multiple contributors to code the software, build the software, and test the software. And after this process, they move to the continuous delivery of these software services, which allows automatic software release and deployment in the distributed, often cloud infrastructure. And together they form the CI/CD pipeline that manage every DevOps and Ops phases in the loop with the automation tools that is applicable. And in the software domain, there are a bunch of tools available nowadays. And the second and third building blocks are infrastructure as code and distributed versioning control system. DevOps makes highly use of this cloud infrastructure to achieve this dynamic and reliable service deployment. And They do this by describing the environment as a code, and they also manage the code under the versioning control system, which is often Git nowadays. On the other hand, in industry, like the automation industry, there are a number of machine-readable data exchange formats to describe these field devices or the functional requirement. And our idea is to use these as an IAC for CPS. Also, data interoperability can be enabled by the semantic descriptions provided by domain-specific models. Other than the ones listed here, maybe we can use a brick ontology, for instance. And having these three elements, we probably can establish CI/CD pipelines to passing through all the phases and also the creation phases of artifact, which kind of gives a structured way of creating this artifact following the requirements in the phases. However, there is one missing. We need interface to mediate the interactions among the engineering executions and this creation of artifact. How do we do this? To this end, we want to use this Web of Things architecture from W3C. And W3C has been developed to counter the fragmentation of the heterogeneity in IoT systems, and which enables protocol-agnostic interaction through so-called thing description. It's a machine-readable data format to describe a thing. And to give you a concrete example, this is a PD describing the installation task of a PLC power supply cable, for instance. So Control L. Control L. Now we go. Okay. Control L. Sorry for interruptions. We have two namespaces which supply the semantic description about this task. And here, this task belongs to this offline and online engineering from automation ML installation task category. And of course, this has an ID, which is a physical file location of this TD. And most importantly, this is protocol agnostic, and this forms defines the protocol that is used to interact with this task, right? So this task requires a documentations. Probably they're taking a picture of the installation of cable, and they can use this OPC TCP binary protocol to upload the documents, for instance. But why thing description? So we use thing description as a proxy for offline and online engineering because it requires a lot of manual work to be done. And this interaction can be done through hypermedia control, which means it is describing engineering task, enabling execution through what is called interaction affordances, which consists of action, event, and property of the thing. And in addition, this hypermedia control achieves the interoperability with other digital twin platforms that can be used in this industry sector. And moreover, TD can be serialized into JSON LD formats, which don't need to be provided by things themselves. And therefore, we can describe the concept, such as the task that should be done by human. And this JSON LD serialization also allows us to annotate semantic description of the types of engineering information. So that in this example down here, we have two domain experts and technicians who interact with this TD described task, which also have the semantic description about different parts. For instance, the cable that is required and which cable A needs to go to interface B and C and so on. And they significantly reduce the time required for humans to discover the thing that you have to use it for the human or manual task. Okay, now stitching them all together, we can have the life cycle of this TD described task. So we created this mock system, and we also applied this proof of concept DevOps system for CPS. And in the upper right, you see the generic pattern of the branching in the Git, in the distributed version control. So we maintain the main channel as a clean branch. Green branch means that branch reflecting the actual shop floor, the current status of the shop floor. And if the system detects the new task is required, then our system creates a new branch that is responsible for specific tasks. And if the new task can be has been executed, then it can be merged to the main branch, and otherwise it's kind of notify the human factors and then reject the merging and then request another task to be done. And then after that, we can merge it. So this cycle starts with task extraction. And this is making use of IEC of this CPS. So in this example, we have PLC for this robot here, down here. And automation ML, for example, is the description language about the field devices and also the interface that exists on the factory cell in this case. We have line 1, cell 1, and all the power supplied in Ethernet plug interfaces and robotic arms. And by analyzing this topology, we can derive the required task to be done by humans. And after identify the required task, using also the semantic description, we can move on to the second step. Second step consisting of two parts. First, our system, we create the new branch for this task. And at the same time, we create this system actually creates the new TD that is corresponding to the task newly discovered. After this, the information system takes this TD and assigns this task to a specific person. And in order to identify this technician, we also use this E-class vocabulary and look up the appropriate person, appropriate technicians in the human laws that is registered in the company. After the technician receives this TD or task, then this technician do the physical execution of the task, actual cabling, power supplying, and also consume this TD action through some client applications. And this application can consume TD and know that the technician has to document what he has done or she has done. And given this feedback to the system, and the system also detects, okay, this TD's action has been consumed, and we received this new artifact. And this triggers the automatic validation with the test with the CI tool that we develop, or if necessary, it requests another manual inspection and approval by the domain experts. So it can be done automatically, or we can also request another humans to inspect the execution of the task. If everything is all green, then we can finally resolve this task and merge it into the main branch. And this is the very structured way of doing this with a validation. And also, we can integrate the human and manual efforts in this life cycle. And I also would like to mention two large projects that use DevOps application toward the CPS. And one of them is the Cosmos. It's a EU Horizon 2020 project. And they are trying to use DevOps to develop a software for CPS. And to distinguish the work from ours, they are more focusing on the hardware, using this software to monitor or the executive hardware. And another one, which is closer to ours, is the adeptness. And they are trying to achieve the semantic interoperability and also using the DevOps to detect the faults in the system. But again, we are explicitly focusing on the human factors and integrating this operationalizing process of the CPS, which is fundamental for any sort of cool stuff that is going on these days. But during this research, we've discovered three main challenges. One of them is the task extraction from the data exchange format. And this is feasible, but very specific to the data exchange format or that exchange engineering tools. So we also need to develop the CI tools that is specifically made for the tools that is actually used in the industry. The second one is, as you have guessed probably, it is quite hard to evaluate this system because there is no structured way or no competitive system that enables this kind of things. So we are thinking about inventing a new metric, something like code coverage in the DevOps for CPS that can maybe take care of the semantic description of the shop floor and compare the TDs that can be submitted in the repository, and then somehow calculate the coverage of the integrity of the system. Lastly, knowledge documentation and clean usage of Git themselves are quite challenging, even for software engineers. So to support this aspect, we want to provide a descriptive but yet constrained user interface or intuitive visualization to help humans to use our system. In conclusion, so we presented this DevOps for supporting the work of multidisciplinary engineering team involved in conceptualizing, installing, configuring, and commissioning reliable industrial CPS. And we also use sync description, which integrates physical or manual engineering task execution into CI/CD pipeline using existing automation tools and data exchange format, meaning that we can utilize legacy tools and yet we can coordinate the execution task. In the future, for the outlook, we are looking into the more quantitative evaluation of total cycle time of task executions, or like the total execution number of times that it took for the CI tools. But it's kind of also hard to compare with the existing CI module because there is no such thing exist today. So we are trying to also establish the baseline system using traditional approach, something like business process modeling language. And that's the future. And that's what we are currently working on. And this is the end of my presentation. And I'm very glad to have your question or grab me during the lunch or coffee break. And by the way, I have 1 minute. So this is different angles viewing our system. So I showed this life cycle of TD described task, but this is more data point of view. So the domain experts developed this automation ML in their domain specific tools, which is running on Windows. And then we have this continuous integration platform running also in Windows because this uses the .NET framework. And then they bypass it to some CI tools running on Git platform, in this case, GitHub. And then it can create some branches and then notify to the human users. And if necessary, go back to the editing of this artifact. Thank you so much.
Thank you very much, Yuri. Are there any questions in the room?
Yeah, it's a very interesting and difficult problem, as of course you have discovered. I'm wondering how much of this is applicable. It looks to me like quite a lot to, let's say, the building management and commissioning process. Like he was talking in his talk, for example, for automating creation of the building schema as it's installed so that applications can use it.
So right now, we are more focusing on the operationalizing process, like building from scratch. And they need to design this building facility fast, and they also want to install this building automation component. And as a consequence, we probably, especially in the process automation scenario, they are looking into more flexible factory. And in that case, maybe they need to relocate this robot and so on. And this task that requires human efforts, like drilling into the in the floor, or like recabling it, or recreating the cable and so on. So, and only after that, the software, like the online engineering, can be achieved. So our focus is more about these foundations that enabling this like dynamic orchestration of microservicing and the building management and so on. And in that sense, this kind of ecosystem that we create is applicable to almost all the CPS, not necessarily building, but also for the supply chain management, where they need to put this RFID antenna and then collect the data. And in order to identify this data collector and deploy it into somewhere in the server, and this whole process can be integrated into the CI/CD pipeline, and which also create a new kind of new job, which is only nowadays done by software engineer, but software engineer can come into this field so that they can use their knowledge and skills to help these field technicians.
Thank you, Yuri.